We are very happy to have Professor Rolf Pisarski from Brookhaven National Lab to give today's colloquium. Let's start with some biographical notes. Professor Pisarski did his PhD in Princeton. Then he had several posts in top institutions like Yale, UC Santa Barbara, or Fermilab. And then since 1989, he has been in the Brookhaven National Lab in different posts, including he has been head of the nuclear theory group. He has been deputy director and deputy group leader of the Riken PNL Center. And he's also a fellow of the American Physical Society. Professor Pisarski's research has shaped our understanding of thermal physics for gauge theories, and in particular for QCD. He has done many seminal contributions in this area, including the understanding of instantons at finite temperature, the perturbative structure of gauge theory plasmas. He introduced the hard thermal loops, which is the standard analysis tool to understand the dynamics of hot QCD. He has worked on many different areas related to QCD at finite temperature and density, including chiral symmetry restoration, deconfinement, and also on the structure of the QCD diagram. And from his post at BNL, he has been had a very important view on the new picture of the hot QCD plasma, or the Quark-Gluon plasma, that has emerged after RIC, and that has been confirmed at the LHC. And today he's gonna, with this interesting title of the Ugly Duckling and the Swan, he will tell us about there's new findings of this new view of the Quark-Gluon plasma that has emerged from these experiments, and also what the 21st century might come for the field of hot and dense QCD. So let me give the floor to Rob, and
Thank you very much for that kind introduction. Let me say at first that there are several people, such as Professor Casal Del Rey, Professor Mateos, Manuel, Tolos, who are working on this field. So this colloquium hopefully will give you, it's not meant for the people working in the field, and hopefully will give you some idea of what QCD is and why we think something interesting happened about 20 years ago. So the moral of the story is how an ugly duckling turned into a beautiful swan. And the idea is that what happened when you went to collisions of heavy ions at very high energies, this is a cartoon. So the energies are so high, in some scale, this is 15 Fermis across. You don't have to know what a Fermi is, but the width is about right, that the energies are so high that instead of being 15 across, it's only a quarter at the accelerator that was built at Brookhaven National Labs, where I'm at, the Relativistic Heavy Ion Collider, or RHIC. And it's about a tenth at the Large Hadron Collider. And so what I'm going to argue is that we have strong evidence for a qualitatively new state of matter. I'll call it a Quark-Gluon plasma, and I'll describe for you what that is. I won't have definitive evidence that it is a Quark-Gluon plasma, but it's certainly that it's a new state of matter. There's an experimental observation that's interesting, that the total number of particles in the collisions is about equal to the number of experimentalists. So it's about 1,000 at Brookhaven and about 10,000 at CERN. And if you look at this, at the cost, it's really about $1 million per experimentalist. And that's true as well with LIGO, and I was discussing this morning with the Gaia experiment. It's really kind of, within a factor of 2, it's about right. And so the moral is, of course, that being a theorist, that we're much cheaper. We can be had for much less than this amount. So this is an outline of the talk. What I'm going to tell you about is the modern theory of nuclei, or quantum ChromoDynamics. So if you haven't heard of it, hopefully you'll have some idea. But if you want the basic takeaway, what we're going to be talking about are things at literally 1 trillion degrees. So if you go home and somebody says, so what did you hear about today? I heard about hot stuff, 1 trillion degrees. 1 trillion is 1 trillion here, right? It's not that million, billion thing. Anyway, you'll see. The experiments you could look at is you could collide 2 protons together. That's PP collision. A proton with a nucleus, A refers to a nucleus with atomic number A. And the nice thing about this kind of nuclear physics is you just want to have something where A is as big as possible, or nucleus-nucleus collisions. And what I'll refer to as the ugly duckling are experiments that were at before Rick turned on. And let me emphasize that it wasn't because the experimentalists weren't doing a good job. It wasn't because of anything like that. It's simply because they weren't dedicated experiments with a dedicated beam. That's really what changed when Rick turned on. So this was results at the AGS at Brookhaven. Also, you don't have to know what the acronyms stand for. You just have to know where they are. This is actually alternating gradient synchrotron, but it doesn't matter. SPS, I forget what the SPS is at CERN, but there was definitely evidence for something qualitatively new happening. And then when Rick turned on in 2000, then there was overwhelming evidence, and I'll describe for you 2 things that are particularly noteworthy. This has been confirmed by experiments at the Large Hadron Collider at CERN, both in nucleus-nucleus and in proton-nucleus collisions. So as I said, it's strong evidence for a qualitatively new state of matter. Maybe it's a Quark-Gluon plasma. That's hard to establish definitively. At the very end, I'll briefly discuss a new ugly duckling. As I said, we found something new as we went to higher energies, and now what's of interesting is going back down in energy. And I'll describe for you what that is related to, but it's in the end, theoretically, I think what will be one of the great problems of theoretical physics in the 21st century, and that is solving the sign problems, the behavior at non-zero chemical potential. Okay, so let me first of all, for those of you who don't know what gauge theories are, explain to you them in a very brief manner. So you all know about electromagnetism. Electromagnetism, you have Coulomb's law, Ampere's law, and the like. But in fact, it's more useful to think of it not in terms of the equations of motion, but in terms of symmetry. So the simplest symmetry that you can have is just say a particle on a circle where you go around by 2 pi and you come back to the same place. That is, it's like a phase. This is what's known as a U1 group. And it's clear that if you just have rotations, that the order of rotations doesn't matter. If I have theta 1 and then theta 2, it's the same as vice versa. This is known as an abelian group after the Norwegian mathematician Niels Abel. And what is a rabbit out of the hat is that what electromagnetism really is, you have this hidden phase, and you can rotate this independently at each point in space-time. And this really is a subtle concept if you're not familiar with it. It's just something you have to take for granted. And this is where really photons and the like all come from. Associated with the fact that the order of the rotations doesn't matter is the fact that electric charge is an integer. We know we either have 1 electron, 2 electrons, 3 electrons, and we can just add them together any way we want. Okay. This then gives rise to the theory of quantum electrodynamics. This was awarded the Nobel Prize in 1965 to Richard Feynman, Tsunetoru Tominaga, and Julian Schwinger. And this is, in fact, the entire Lagrangian of the theory. I'm not going to go through the details. A mu is the gauge field, psi is some charge field. It's simply that you can write it down in one line, and it has a very simple form. It doesn't mean the solution is simple. And the fact that this is a gauge symmetry tells you that the photons are massless. Again, that's not obvious, but it's a consequence of this local gauge symmetry. What's useful is that in this theory, the coupling constant is very small. The fine structure constant is about 1 over 137. And this is a picture from of Julian Schwinger, and he said a theorist only needs pencil and paper to compute. And of course, as I had earlier, he also needs coffee. And this is a picture of Schwinger's tombstone. It was, all it has, doesn't mention Nobel Prize or any of his other accomplishments. There's just one thing, alpha over 2 pi. That's this alpha. So why is this on his tombstone? Well, it turns out to have been the first successful calculation of a radiative correction in this theory. And it was something that he was evidently very proud of. He predeceased his wife, so I presume she had his, that's what he wanted. Anyway, instead of considering an abelian gauge theory, you can also consider a non-abelian gauge theory. Now, this was first described by C.N. Yang and Robert Mills, actually at Brookhaven in 1954, and also Wolfgang Pauli in unpublished work. Now, this is the thing, it's a group, like, for example, you could consider the group of rotations in space. This is a SO3 group. If we have a symmetry where we rotate, we have 3 directions we can rotate in. And then the rotations are going to be different because they're matrices. And so it's not going to have the simple property that we had before. What will be true is that because it's a gauge symmetry, because it's this local gauge symmetry, the associated photons are massless. And so for a long time, when it was first proposed by Yang and Mills, Pauli asked, where are the massless non-abelian photons? And it was an excellent question. And in fact, in the 1960s, this theory was generally discounted because there was no such proliferation of massless particles. In 1971 and 72, Gerard and Hooft and Martinez-Veltman showed that in a technical sense, these theories make sense. This is the statement that they're renormalizable, that their ultraviolet properties at very short distances make sense. And in fact, they form the basis of what's known as the Higgs effect, where in the electroweak interactions, the W and Z bosons get a mass, which was responsible for the Nobel Prize to Brout and Higgs in 2010. Okay, so let me go on and explain to you then how this applies to the modern theory of neutrons and protons, which I'll call nucleons. This is a non-abelian SU3 gauge theory. As I said, SU3 is the theory of rotations in space. So imagine that each of my fingers were a complex number. Then that would be like the gauge symmetry. Why it's SU3 is not obvious. That has to do with detailed properties of the theory, but it's some sort of generalization of things that we're familiar with. The non-abelian photons are called gluons. There's 8 of them. And there's 6 flavors of quarks, which are a kind of fermion. That I refer to both color and flavor is simply a nomenclature. But again, you can write down the Lagrangian in one line. I'm not going to explain to you what all of these things are. A mu is the gluon field, Q is the quark field, and I'm ignoring various things. But in analogous to quantum electrodynamics, there's just a single coupling constant, alpha S. What's different is that in the abelian theory, the photons interact with charged particles, but not with one another. Whereas here, the gluons interact both with quarks and with one another. Furthermore, they're not integers as in quantum electrodynamics. They're not numbers, they're matrices. And anybody who's dealt with matrices knows that if you multiply them together, what you get depends upon the order in which you multiply them. So that's why it's a non-abelian theory. The charges don't add, they multiply, and consequently, they don't commute. what's very different from QED as well is that we well know that at large distances, we can talk about the charge of a particle. It may be screened, but it's a well-defined concept. In contrast, in QCD, it only becomes simple at short distances. This is the property of asymptotic freedom, where the coupling goes to zero, not at large distances, but at short distances. This is because gluons interact with one another. It's unlike any other theory. And this was first pointed out by Gross, Politzer, and Wilczek in 1973, for which they were awarded the Nobel Prize in 1974. This is a graph of the strong coupling constant alpha S versus momentum. Momentum is like 1 over distance. So as you go to high momentum, it goes to the coupling constant becomes small. And it does so, in fact, logarithmically. And now calculations have been carried out to very high order. Okay. The problem is, how do you compute at large distances? We want to know the behavior. And clearly, Schwinger's admonition to use pencil and paper isn't going to work. Now, the answer was first proposed by Ken Wilson in 1974. He said, well, you put the theory on a lattice with a lattice spacing A. And by asymptotic freedom, you must get the right result in the continuum limit as the lattice spacing goes to zero. Wilson was awarded the Nobel Prize in 1982 for, in fact, the renormalization group, which underpins this. But what's interesting is that he proposed this theory a few months after the result of asymptotic freedom. Now, in the 70s, Wilson said there's no point in bothering with numerical simulations because it was going to be too hard. And this is a picture of my colleague, Mike Kreutz. He, in fact, doesn't usually show up in the office in this manner. This is when he was on vacation at Club Med, I think, playing Poseidon. But those of you who know Mike know that he doesn't normally dress much more formally than this. And in fact, if I can say, he was up for tenure, and people said, no, there's no point in doing this. It's useless. And he's like, well, why not try? And what he was able to do is to show that you have confinement on very small lattices. And today there are some results that are very close to the continuum limit. So this result really, by not listening to the graduate students in the audience, sometimes you shouldn't listen to those who you think might know better. Okay. So what does confinement mean in detail? We know that in electromagnetism, you just have a Coulomb potential. So the lines of flux spread out. And what happens is in QCD, at very short distances, you have this kind of Coulomb potential. But then at large distances, you get a constant term in the potential. So eventually, you can't pull an individual quark apart. The only thing that you can measure are gauge invariant color singlet states. So that's what happened to all of these massless non-abelian gluons that bothered Pauli so much. They're all confined. This is a picture of a quark and a quark. This is a picture from Derek Lineweber. And this is the flux string forming between the quark and a quark. This is believed to happen. We have numerous simulations from the lattice. But there's $1 million prize from the Clay Institute if you can come up with a proof of this. Okay. So that was a brief introduction to what non-abelian theory is like. Let me now tell you what happens with a plasma. So what is a plasma? Well, a plasma is where you either dump temperature, you heat up a system, you put in, say, a background electric field such that the charges are able to move independently. So for example, for an atomic system, you could heat it up, and if you, in the fluorescent lights here, you put an electric field and the positive and negative charges move independently. What then happens was first pointed out by Peter Debye. If you put in a test charge, say a test positive charge, electric negative charges are going to move to screen it. And so the at long distances, the Coulomb potential is going to be screened. Instead of just getting 1 over r, you're going to get an exponential damping by a quantity known as the Debye mass over distances on the order of 1 over the Debye mass. And if you go to very high temperatures, this is a very simple form. And it's simply the Debye mass squared is the electromagnetic coupling constant times temperature squared. And for this, Peter Debye received the Nobel Prize in 1936. You can then do this in a non-abelian plasma. As the temperature goes to infinity, as I said, the coupling constant vanishes logarithmically. So as the temperature goes to infinity, QCD should become some kind of ideal gas of quarks and gluons. This is what the Quark-Gluon Plasma is. Simply as you go to infinite temperatures, it's weakly coupled. It's got to be some sort of plasma. You can then generalize the concept of Debye screening. The term looks a little bit more complicated. I'm not going to explain this. But again, what's interesting is that you can write down the leading term. This is a generalization of this term. This is a bit misleading. This is, in fact, for static fields. But in any case, to a non-abelian theory. And in fact, there are recent generalizations to this to higher order by a Finnish group, by Tyler Gorda et al., and also by Cristina Manuel and Stefano Carignano, who are here now. So what they've looked at is higher order corrections in the coupling constant squared to this. But it's a nice way of organizing perturbation theory. Okay, but this is what happens at infinitely high temperatures. Clearly, we're not going to reach that. So what might we expect to happen as you go down in temperature? Well, in that case, it's interesting to consider a gauge theory with an arbitrary number of colors, NC, and some number of quark flavors, NF. And Gerard 't Hooft, who was responsible for showing the renormalizability of gauge theories, said it's useful to consider the limit where the number of colors goes to infinity. Now, I haven't told you really in detail what it is, what the matter content of an SUNC gauge theory is, but the point is that there are NC squared of them, because it's a matrix. It's an NC by an NC matrix. So the gluons are going to have degrees of freedom proportional to the number of colors squared. And then if it's high temperature, it's going to be T to the 4th. In contrast, the quarks are like columns in an SUNC gauge theory. So there's just NC times NF of them. NF is the number of flavors. They're just like duplicates. So in all, you're going to have something that's proportional to the number of colors squared. In contrast, at low temperature, because of confinement, as I said, we only have color singlets. So the pressure has to be of order 1. It can't involve the number of colors anywhere. So if you have a pressure of order 1 at low temperature, a pressure of order NC squared at high temperature, then you'd expect there'd be a phase transition between them. And in fact, this is the deconfining phase transition. So you can rigorously define in a pure gauge theory the difference between a confined and a deconfined phase. There's, in fact, a more precise definition that I'll mention. Okay, this is some aside for group theory. For those of you who are interested, I'll just flash that by. But what you can then argue is that the pressure divided by the number of colored squareds times T to the 4th, well, it has to go to the Stefan-Boltzmann law at infinitely high temperature. And the pressure is of order 1 in the low temperature phase, so it's 1 over NC squared, since I've divided by NC squared. So you can clearly see you go from a phase with very little pressure to a phase with a huge pressure. And remember, this is divided by T to the 4th. So if I had the absolute pressure, it'd just be huge. And so what you can do is you can think, well, maybe I can come down in perturbation theory. This is a long story. I'm not going to go through this. But it turns out that coming down in perturbation theory is a very hard job. You have to resum, and it's not a simple thing. Okay. So I have to give you some idea of what QCD is like. The proton and neutron that you're familiar with, I'll use units where this mass is 940 MeV, which is about a GeV. And as I promised, this is about 1 trillion degrees. There are different flavors of quarks. There are 2 very light up and down, and one that's sort of light to strange. And these will principally be what I'll talk about. Because these are very light, there's a global symmetry associated with this for which you get Goldstone bosons. And these turn out to be the particles known as pions, kaons, and the like. So these are almost Goldstone bosons from the breaking of this global symmetry. There's other quarks as well. There's charm, bottom, and top, but these don't tend to matter. Okay. So if you break the symmetry at low temperature, this chiral symmetry, you expect to restore it at high temperature. This is just like the magnetization in a spin system. So you'd expect I have some non-zero VEV, and then at some point it drops to zero. This is if the chiral symmetry were exact. And you expect it to be, on general grounds, a first-order transition, at least for 3 light flavors. There's also a deconfining transition. I won't go into the details of this here, but there is an order parameter. What's interesting is that the order parameter is reversed. You notice how this is non-zero, and then it jumps to 0. This is the converse. It's 0, and then it's non-zero. This is basically related to the free energy of an infinitely heavy test quark. And we also expect this to be first order on general grounds of symmetry, simply because there's 3 colors, as pointed out by Ben Svetitsky and Larry Yaffe. Okay. Well, but we need to know what happens in QCD, where we don't have pure glue. So you can plot a phase diagram if you have the mass of the up equals the mass of the down quark and the mass of the strange. We know it's first order up here, where there's infinitely heavy quarks. We know it's first order down here, where there's very light quarks. And the question is, where does QCD lie? And it turns to lie in a region where you just have crossover. It's not in either first order region. It could have been, but it's not. So this is where the lattice can help us. The lattice shows that if we plot the pressure over t to the 4th, so remember, we're dividing by t to the 4th. This has to go to the Stefan-Boltzmann law, that we have a small pressure at low temperatures, and then it slowly approaches the Stefan-Boltzmann law. This blue band refers to the uncertainty in the lattice results. So you can see the lattice has given us really essential information that we wouldn't have had otherwise. And it's a real triumph for the theory. We know that there's the behavior of the pressure is a function of temperature, and you can also estimate where the crossover occurs. Now you might say, well, it's crossover, it's just smooth. But the point is you can plot what's known as the chiral susceptibility. I won't describe this in detail. It's the derivative with respect to a mass parameter. But there's a function that has a maximum at a very precisely defined point that tells you that the chiral transition happens at about 156 MeV with an error of approximately 1%. So at least according to the chiral properties, we have a well-defined point at which we expect a qualitative change in the theory. You can ask what happens. Oh, excuse me. That's embarrassing. To the deconfinement. And again, this is results from the lattice. And in the pure gauge theory, you have a strict order parameter, so it's 0 and then jumps. But in QCD with dynamical quarks, it just smoothly evolves. But the phase transition is way down here, and you notice it still looks pretty confining if you look at this order parameter. Okay. Well, this is results of what we expect from theory. So yes, there's no true phase transition, but there is a huge increase in pressure. The system's expanding rapidly, and basically what's going to happen is it takes a long time to burn off the entropy, and so we can tell that we have probed the new phase of matter. So now I'm going to go on and describe to you what happens experimentally. So the basic variable is the energy per nucleon in the center of mass. This is all going to be measured. Remember, the proton weighs about a GeV. So it's all going to be the energy in the center of mass. This began at the AGS at Brookhaven at energies of about 5 GeV. At the SPS at CERN, it ran from 1986 until the present at energies of 6 to 20. And then with Rick in 2000 at energies of actually 3 to 200 GeV. And the LHC from 2009 at TeV. So this is a TeV is 1,000 times a GeV. These experiments, the AGS and SPS, were fixed target. That is, you had a beam hitting something and then you measured what came out. That's useful because you get high luminosity, but you don't have full coverage. Both Rick and the LHC are colliders. That means you have two beams that come at each other in opposite direction, and then you have very good coverage with some cost in luminosity. Okay? The reason why you want to go to higher energies was first suggested by James Bjorkane, who I think should have gotten a Nobel Prize with 't Hooft and Veltman, and probably won't, but for other work leading basically to asymptotic freedom. But what he noted is the following. This is kind of a complicated graph, so I don't want you to concentrate too much on it. What he pointed out is you go up in energy, a plateau will emerge. And remember I showed you that flux tube where you have a quark, antiquark, and you pull it apart and you get a flux tube? What basically happens is if you look at the number of particles per unit rapidity as you go to higher and higher energies, this is energies of 20 times the mass of a nucleon, 130, and 200. You get some region where the particle number is approximately constant. The rapidity is something like the momentum down the beam. It's a relativistic invariant. It's more complicated, but the difference doesn't matter. What Bjorkane pointed out is that very high energies, this plateau will emerge, and moreover, that it will be free of, basically free of baryons. The baryons, the baryon number that you had in the initial nuclei are going down the beam. They're concentrated down the beam here, and this region has a very small number of net baryons. So it's clearly a new regime, and he developed a boost invariant ideal hydrodynamics for this plateau region. Okay, so the first experiment in which you had a collider of heavy ions is at Brookhaven. So the heavy ions are produced in a tandem. They then go to the alternating gradient synchrotron, and then they're injected into this ring, which is about 1 kilometer across. And you might think this was a very intelligent, sophisticated progress of physics, which is completely wrong. This tunnel was built because it was going to be a proton-proton collider that was canceled in 1983. It was canceled because the US was going to build a superconducting supercollider. Instead, that was canceled a decade later. And what happened is in 1983, in a few weeks after the Isabel Collider was canceled, Nick Samios, who was then head of Brookhaven, talked to people like T.D. Lee, Gordon Bain, Larry McLaren, and others, and proposed turning it into a nucleus-nucleus collider. And that turned out to be a very prescient decision. And I must say that at the time, the ideas for what you'd find in a Quark-Gluon Plasma were really a little crazy. T.D. Lee really pushed this, in particular, because of various ideas that have all turned out to be wrong. But the basic idea of building a dedicated machine where you could really study this phenomena turned out to be correct. Now, fortunately, in Europe, you're much more rational about things. You went from the proton synchrotron to the super PS and onto the LHC. So this is a picture from the, I believe it's from Elise, of what things are like. It's a wonderful animation. So you have a much bigger ring. You have 7 TeV on 7 TeV. This is the equations for the Higgs effect, and this is going to show you what the collisions of two nuclei look like. I'll let it run because it's really a beautiful animation. And as I said, you're picking out collisions with many thousands of particles, and it's quite a triumph that in this complicated environment that experimentalists are able to pull out interesting properties of the collision. So you have this very high multiplicity regime. How do you tell what's going on? Okay. Well, let me first review some of the hints we had that there was something new. One was at the SPS, where you look at what's known as J-size suppression. One of the types of quarks was a charm quark. This is relatively heavy, and it's so heavy that it's really bound by a Coulomb potential. And a suggestion by Tetsuo Matsui and Helmut Satz in 1986 was that because of this phenomenon of Debye screening, that in a plasma, the Coulomb potential would be screened, and so the bound state would disassociate. And this was found. The J-size and nucleus-nucleus collisions are suppressed relative to proton-proton. This is a somewhat complicated graph of J-psi cross-section over drel-yen. You don't have to worry about it, but it clearly shows suppression. And this suppression has persisted at RIC. At the LHC, it's not as strong, and so there's clearly also regeneration going on. The J-psi disassociate, and then they find each other again. But I just want to emphasize, to give due credit to the results from CERN. They also found an enhancement in dileptons. This is where you create virtual photons, and they go to either electron-anti-electron pair or a muon-anti-muon pair. And you see an enhancement over what you'd expect from simple extrapolating from proton-proton collisions. And this, again, has persisted both at RIC and the LHC. And in fact, it seems to persist at lower energies as well. Okay, but let me go tell you what things are like after RIC turned on. This is a picture of the Great Wave off Kanagawa by the Japanese artist Hokusai. And it's really, there's just this enormous amount of experimental data that us theorists are sitting in this kind of rickety little boat trying to understand what's going on. In general, I think the results agree qualitatively at kind of zeroth order, but making detailed comparisons turns out to be very challenging theoretically. Okay, so what happened in going from the SPS to RIC is that it's a higher energy and a baryon-free plateau emerged. You also had dedicated detectors, high luminosity. Before RIC turned on, people said that, well, nearly hydrodynamics is not going to work well. We should fit to parton cascade models, which are like little billiard balls. And all of these predicted a huge increase in multiplicity. From day one at which RIC turned on, there was no large increase in multiplicity, and all these models went by the wayside. And it was seen that nearly ideal hydrodynamics in a boost invariant form worked pretty well. So there was a complete change of paradigm. It's clearly a new regime. As I've mentioned, it may be the Quark-Gluon Plasma, but that's difficult to establish firmly. It looks like it. And then results from RIC to LHC are essentially consistent, although there's one novel feature that was seen. So these are the pictures of the star at Phoenix experiment, which star finished running. Phoenix has now been upgraded to S-Phoenix. There was also Brahms and Phobos. The LHC experiments are Elise, Atlas, and CMS. And you can see these are so large. Elise has something like, what, 1,000 people? That, you know, there's one person. There's no point in getting all 1,000 people. CMS and Atlas are thousands of people, right? Something like 3,000 to 4,000. Okay. One thing you can say, well, is it thermal? Well, one thing you can ask is, well, if I have a system at a given temperature and a given chemical potential, I can look at relative abundances. And this is a plot due to Peter Braun-Munziger, Joanna Stackel, Christoph Redlich, and Andronich, in which they look at this. This is from the Large Hadron Collider. So they take one parameter, a temperature. The chemical potential is basically zero. And you look at the relative abundance of pions, which are the lightest particles, down to, look at this, anti-helium-4. And it appears to fit. Now, there are things that are left off of this graph that you might ask about. But still, this plot was once described as the most interesting, boring plot he'd ever seen. I mean, you know, all you have to do, you know what a Bose-Einstein or Fermi-Dirac distribution is. You plug in these two numbers and you get out all of these results that vary by what? 9 orders of magnitude. So clearly, the idea of a temperature is not nonsensical. You might ask, though, if you're a theorist, this is an example of where at 0th order, things work great. And then you think about it, wait a second. You know, it's not just going to cut off at one temperature. Things are going to interact. The system is still expanding. And pions are certainly going to interact differently than anti-helium-4. So why does one temperature work? And this is an example of what will happen. To 0th order, everything looks great. And then you think about it, and it's really surprising. So what I'm going to tell you about are two things. So this was a long introduction. Now I'm going to tell you the two things that are particularly memorable in heavy ion collisions. One is elliptic flow and producing the most perfect fluid on Earth. And so what you can ask is, you know, these nuclei are big. They're like 15 Fermis across. Fermi is a nuclear dimension. And most of the time, they're not going to hit each other exactly. Most of the time, they're going to graze each other. It's going to be like some shoulder. So where they overlap will be some hot region, and then you'll have a lot of cold spectators that just keep going down the beam. So you can look at the difference. You start out with a difference in space between, this is an almond, between the long part of the almond and the narrow part of the almond. And if you have, if they're just free streams, that's all you're going to get. But if there are collective effects present, this object initially is going to become spherical, whereas in momentum space, it starts out like this, but you can see in this narrow part of the almond, it's not going to have far to go, whereas here it's going to have far to go. So you're going to end up with a difference in the momenta in this long part of the almond versus the short part of the almond. And you can use nearly hydrodynamics, nearly ideal hydrodynamics. The basic parameters here are the shear and bulk viscosity relative to the entropy, which are dimensionless quantities. I'm not going to describe nearly ideal hydrodynamics for you. I'm simply going to show you the results. This is from my colleague at Brookhaven, Bjorn Schenke. So you obtain, remember, there's lots of particles about. So this is, you know, there's thousands. This is over the entire solid angle. So you can fit in some distribution relative to the reaction plane. You have so many particles that you can certainly tell where this short part of the almond is. And then you can simply do a Fourier decomposition to measure these coefficients of elliptic flow. And you can then see what you get out. And this is results from the Jetscape collaboration. And there are fits to both the shear viscosity over the entropy versus temperature and the bulk viscosity over the entropy versus temperature. And there's clear evidence for the fact that you have a small shear viscosity, about 1/10, near the chiral transition. That increases. These are Bayesian fits, so it's not, it's a difficult job. But there's certainly evidence that this quantity is small near the phase transition. Now, what do you expect perturbatively? Well, somewhat counterintuitively, if you're in a weakly coupled system, the shear viscosity is large because it takes a long, if things interact weakly, it takes a long time for them to communicate with one another that they should thermalize. You can compute this in perturbation theory, and in fact, the shear viscosity over entropy goes like 1 over the coupling constant squared. The bulk viscosity is smaller because it's related to the breaking of conformal symmetry. This is an example, unfortunately, where the lattice has a very hard job of doing, because these are quantities not in thermodynamic equilibrium, but near. And so presently, we only have very preliminary results. But if you plot where heavy ions are and compare it to other systems, such as water or liquid helium, it's really significantly smaller. Now, I should say the shear viscosity in these systems are huge. It's about 10,000 times that in pitch tar, but the entropy is also small. And so if you look at the ratio of the shear viscosity over the entropy, it's about 1/10, and it's much smaller than anything else, and so it's why we call it the most perfect liquid on Earth. And as you can see from my previous, this graph here is suggestive, but it certainly has to be a small value. A lot of excitement, which Professors Casaldere and Mateos have worked on, is how you naturally could get a small value of eta over S. This was due to work by Juan Maldacena, who posited a duality between the most supersymmetric theory with an infinite number of colors and string theory on a certain manifold. And it's known as the ADS-CFT correspondence. This duality enables you to compute for infinite coupling in a gauge theory with an infinite number of colors using a classical supergravity. Now, this is a different theory, but what's interesting is that in this theory, you find that the ratio of eta over S is 1 over 4 pi, which is very close to 1/10. And Son, Starinets, and Kovtun suggested that this is, in fact, a lower bound. And so it's an example that this value is very close to the bound from ADS-CFT. ADS in 2 dimensions. This is a picture from the Dutch artist Escher, and this is a self-portrait, and I've superimposed Juan Maldacena's picture on that. Okay, so there's clearly evidence that the shear viscosity is very small. The other phenomenon is that of jet quenching, and so let me describe that to you. This is basically how the Quark-Gluon Plasma eats jets. So what I've been talking about with hydrodynamics are most particles which are at very soft momenta, energies less than 1 JeV, which is the mass of the proton. By asymptotic freedom, though, in QCD, hard particles are distinctive and form jets. And so this is a plot from the of a electron-positron collision that forms 2 jets. This is like quark-antiquark forming. You can also see a quark-antiquark if you look hard plus a gluon. But if you go to very high energies, you should see the quark coming out. It propagates for a long time, and then it hadronizes, and you see that soft spray. The idea of jet quenching is really very simple. Say if I'm running in air, I can certainly run fast. There's not much air. If I were to try to run in a pool of water, I'd run a lot slower because I have to push the water out of the way, and pushing the water out of the way is going to make a big wave. That's basically the idea of jet quenching. In a proton-proton collision, you have a quark-antiquark produced. They emerge without much interaction, whereas in a nucleus-nucleus collision, there's a lot of stuff to go through. This was, in fact, pointed out by Brookhaven in 1982. And then there's lots of other work which has been done, including by, again, Professor Casal del Rey, who did work on using holography in the ADS-CFT correspondence. Okay, this is a picture of it. This is something that's really emerged from LHC, is being able to look at this jet quenching at very, very high momenta, because the energies, you might say, well, you know, the energies are, what, 100 times greater. The difference in temperature isn't that high, because the energy density goes like something like T to the fourth. So you don't see a striking difference for most soft particles or hydrodynamics. What you do see is you get a lot more hard particles coming out. And so you can easily measure to much higher transverse momenta. So this is a plot from the CMS collaboration. You have a leading jet at 200 JeV and an away side jet at 70 JeV. And it's just clear you have to have momentum conservation. So this thing started out with something like 200 JeV, and what's happened is the away side has been eaten by a lot of the stuff. So what's happened is one of this 200 JeV jet must be near the center here, and it goes out without significant interaction, and the 70 JeV goes a long way through. Okay. At RIC, it can really only easily measure particles up to about 20 JeV. A new detector that's running now as Phoenix will measure up to 40 JeV. But what you can do is plot the ratio between the number of particles in nucleus-nucleus collisions to that in proton-proton. And what you find is that this ratio is less than 1. This is the phenomenon of jet quenching, that it's harder running through a pool than running through thin air. So this is the plot of the number of particles from leading hadrons, and it's about 0.2, and it goes up to about 20 JeV. The purple dots are direct photons, and those shouldn't feel the effect of the medium since they only interact weakly. And so that's about 1. So this gives you an idea. You have to divide by this number of particles. That's a somewhat subtle thing that they've gotten the normalization right. And you see this goes up to about 20 JeV, and it's really flat. So until the Large Hadron Collider turned on, people thought, oh, this is proof that ADS-CFT is going to work all the way up to high energies. This is going to be great. It's just going to be flat. And when the LHC turned on, this disappeared. You see, rather surprisingly, jet quenching up to hundreds of GeV. This is a plot of 0 to 10% are the most central collisions. 30 to 40% and 60 to 70 are more peripheral, where you have a smaller element created. And so you'd expect to see less effect of the matter. But you're still seeing significant jet quenching. This is probably due to the fact that you're not defining a jet properly. And there's a lot of work going on to really define a jet properly and distinguish between a nucleus-nucleus collision and a jet and a proton-proton collision. But this is telling you, look, even at this values, it's about, what, 0.6. It's practically 900 GeV. It's really quite interesting, and there's a lot of experimental interest going into this now. Okay, as I said, the future of jet quenching will be studied further by S. Phoenix. There are other features that are somewhat surprising. In QCD, the scattering of light and heavy quarks is different. At LHC, there's recent evidence for the difference you'd expect to see for heavy quarks, in particular for bottom quarks, is seen. One question that I have is that you would expect that you should be able to tell the difference between a quark jet and a gluon jet. This is a very hard problem that I think will have to eventually be addressed for us to claim that it's really due to jet quenching. Basically, this is a matter that the quarks and the gluons have different charges. The different charges should be screened, should be quenched differently. Okay. So in other words, Well, okay, let me go through this joke. I think I would argue that we have created a qualitatively new creature. It's like a unicorn. It's no longer a myth. Whether or not it's a Quark-Gluon Plasma is another question. This gives rise to the bad joke, which is a little bit in poor taste, perhaps. If the Quark-Gluon Plasma is a unicorn, experimentalists are, of course, hunters, then theorists are the only other creature remaining in this diagram, and I'll leave it at that. I didn't have time to cover other things. I didn't have time to cover the chiral magnetic effect proposed by Dima Karjaev, Larry McLaren, and others. Let me mention one other thing, though, that is very interesting, and that is, before Rick turned on, people were wondering, oh, things wouldn't look like they equilibrated, just be a mess. You wouldn't learn anything interesting. Experimentally, people have looked at proton-nucleus collisions or even proton-proton at very high multiplicity. Typically, you get about 5 particles per unit rapidity. In these cases, they can trigger about 1 in a million events where you have, instead of 5 particles per unit rapidity, 50 or 100. And it really does look like a little bit of the Quark-Gluon Plasma. In particular, it seems to obey a nearly ideal hydrodynamics, but you don't see jet quenching. But the fact that you would see this in, say, a proton-nucleus collision, even at high multiplicity, was very unexpected. Okay, I have a few minutes left. Let me just tell you that one or two things about why I and others think it may be interesting to move back down in energy, and the connection to neutron stars. So, well, I don't want to describe this in detail. Basically, the problem is that the lattice can compute at 0 chemical potential, but if you go to non-zero chemical potential, it can't. Basically, what happens is you're flipping a coin, and if you're at non-zero chemical potential where there's a sign problem, you're flipping a coin with an imaginary potential. This is the sign problem, and it's ubiquitous in many areas of physics. This is in principle solved by quantum computing. What quantum computing does is basically you're just computing a sum over states, and there's no imaginary term because this is just you're computing the sum of e to the minus energies divided by temperature plus the chemical potential times the number density. The question with quantum computers, to be honest, is that, as I said, Mike Kreutz first showed that you could compute in QCD, at least in vacuum, in 1979, when he simulated a gauge theory with 2 colors on a 4x4 lattice. The question, I don't think with quantum computers we're at 1979. The question is, are we at 1969? But if nothing else, for those of you who are interested in a problem which certainly has a future, I think that is applying quantum computing to problems such as theories with the sign problem, the evolution in real time, that in principle cannot be addressed by classical computing. Okay, you can in fact use lattice results. The lattice can go out at high temperature and non-zero mu, so it can go out in mu, and you can in fact fit 2 properties and estimate at a given energy what the temperature and chemical potential is like. I'm not going to go through this in detail. I just want to flash one last diagram, and that is what's interesting is to consider the phase diagram in the plane of temperature along the y-axis and chemical potential along the x-axis. As I said, the lattice tells us that at small mu there's a crossover. There's the suggestion that you could have a true critical endpoint in the phase diagram. This would be a true second-order phase transition. This is something that's been investigated by the beam energy scan at RIC recently, and at the Colliders Fair, which is being constructed in GSI. There's also NICA in Russia. But what's very interesting and is related to work that Loratolos and others here are doing is to relate these properties here, which we could reach experimentally, to properties at very low temperature, as can be measured in the collisions of neutron stars as measured by gravitational wave detectors. Okay, I'm not going to go through. There's evidence that we may see something happening in a critical endpoint from the beam energy scan 2 at Rick. I'm not going to go through that in detail. Let me just show you. This is a plot of what this should be the condensed baryon matter experiment that FAIR will do. Basically, it's going to increase the interaction rate by a factor of 10,000. And part of our enthusiasm is the fact that with such high luminosity, this is comparing to the luminosities of STAR, S Phoenix, Elise, at very low energies. We should really be able to have a much better handle on what's going on. And so I think it's well worth doing. And as I said, it's related to the properties of neutron stars. In particular, one thing that has been discovered from the fact that there are very heavy neutron stars is that there appears to be a huge spike in the speed of sound, much bigger than that of nuclear matter at lower energies as produced in heavy ion collisions or for free quarks. And so this is a very interesting area that a lot of us are very excited about. You'll basically be able to tell properties of the equation of state from the gravitational waves emitted after the collision. This is a frequency regime that can't be probed by present-day gravitational wave detectors, but will be in the near future. And of course, LIGO was awarded the Nobel Prize in 2017 for this. Okay. Well, Gertrude Stein in 1890 said that about Oakland, California, that there's no there. And I think that at least for the phase diagram of QCD at low temperature and high chemical potential, that there is a there because of the new experimental efforts. And because I'm a good American citizen, let me end with a paean to my former president. And with that, I thank you.
Thank you, Rob, for the nice talk. And now it's time for questions.
I really like your story about the change of paradigm after it came into operation. I myself was witness to many of those things, but I'm a bit surprised that you didn't mention that the formal statement about the discovery of new state of matter was made before IC based on the SPS data from CERN. Sorry?
Yeah, I apologize. That's why I put the J-psi first. Yeah.
And that was a comment.
Well, no, I actually would still argue, even after Rick, it's hard to claim that we've really discovered a Quark-Gluon Plasma.
Yeah. Therefore, in statement, it was also carefully said that this is a new state of matter. I completely agree with that. And the question is, in one of your transparencies was mentioned that we will need a lot of time to burn all the entropy. What you wanted to say with that?
It's a, I showed P over T to the fourth, and it was a relatively moderate rise. But if you use that equation of state and you use this Bjorkian hydrodynamics, the system really spends most of its time in the region between about 150 and 200 MeV, because it just has this large pressure, this large entropy that it has to get rid of. So it's a relatively small change because what I plotted, because it's divided by T to the fourth. But when you put in the numbers, it spends most of its time in that region.
Is it that related to what is called HBT puzzle? So the time of the transition is very fast. Or
no, because the HBT, Okay, no, thank you for asking that. Before Rick turned on, people thought that it was going to be strongly first order and it'd last a long time at the, at some first order mixed phase. And people worried about Coulomb corrections and the like. Instead, as was shown as that plot of abundances, it appears to turn off very quickly. And what you're mentioning is you can do pion-pion interferometry on identical particles, and you can estimate the time of emission, and it's short. And that's the only way that plot of abundances makes sense. How can the relative abundance of anti-helium-4 look like that of pions unless for some reason it just turns off very quickly? But again, that's an example of the fact that to zeroth order things work out, and then you try to do a better job and it gets much harder.
Suppose that you had any collider you wanted and arbitrarily precise detectors. Is it still possible that in these collisions you may miss, in the search for the critical point, you may still miss it because you can only tune one parameter, which is the energy, in the collision, depending where the critical point is?
Yeah. So at this, in vacuum, you know that we have pions and they're in a chirally symmetric phase degenerate with the sigma, which is a particle which is relatively heavy, has a mass of 500 MeV and a width of 500 MeV. At this critical endpoint, the pions are still massive, but the sigma is exactly massless. And so in fact, analyses using the functional renormalization group find that the region in which you see critical behavior near here is basically within 1% of this point. It's very narrow. So your question is, isn't it going to be, because you start with a collision, it's at some point in temperature and chemical potential, you evolve down. How do I know that I'm going to precisely hit that? And the answer is you don't. Probably what you'll have to detect is not directly this feature, but the first order transition at lower energies. But there is experimental evidence that something interesting is going on. This is a ratio of, it's called kurtosis, of the fourth to the second moment with respect to chemical potential. This is results at square root of S of 7 GeV from star. And this is a result from star in fixed targets mode, which is comparable to Hades. And the argument is that this change in sign is evidence for a critical endpoint. I don't think that's true. I think your comment is valid. I think it will be hard to argue that you go exactly through this point, and that will have, at best, indirect evidence, as I said, particularly from seeing a first order transition at lower. Well, first order transition should be fairly, that one should be able to tell.
But my comment was a bit broader. I was wondering whether you could miss even the line of first order phase transitions. Suppose that the critical point is very deep. It's a
you mean if it's down here? Oh, absolutely.
No. If it's at very high chemical potential.
Oh, yeah, absolutely.
Then
no, and lower temperature, absolutely.
You could just cool down.
Absolutely.
And miss the whole line altogether, right?
Absolutely. There could be no line. There doesn't have to be.
No, but I'm saying, assuming there is one,
yeah.
it could still be impossible to detect.
No, I agree.
Experimentally.
I agree. I basically, my enthusiasm about going to lower energies is not because I believe the theory, but because I think the experiment will give us interesting results to play with. And because of the connections to neutron stars. I mean, as I said, if you were to build Rick beforehand on the basis of the theory was all wrong. Everything we thought was true was wrong. It's an interesting sociological lesson.
More questions?
That gets back to that all something, the other creature in the tapestry.
Any other question? So I have one myself. So what would it take to show there is a Quark-Gluon plasma?
I don't know. You ask condensed matter theorists that, and there's not like a smoking gun, right? That's why I was careful. It's not, if you really ask, how do you know it's a state in thermodynamic equilibrium? It's
What do you call
difficult.
the Quark-Gluon plasma?
Well, you know what, I used to make the joke, didn't, who was it, the musician Prince, the artist formerly known as Prince, so, the state of matter formerly known as the Quark-Gluon Plasma. But if it's a useful paradigm and it seems to fit a lot of the data, then I think it's useful. In that sense, though, determining things like the difference in quenching between quark and gluon jets, if you're really going to take it seriously, then you have to show something like that. It's hard, but
Any other question? Oh, one more. Let's do one more. And
would you be willing to speculate to what extent this program can tell us about the Quark-Gluon Plasma we think existed at the beginning of the universe?
all right, there I'm fairly certain, simply because you have very small chemical potential and you have to cool down through the phase transition. The question there is with the early universe is that if it's, unless for some bizarre reason it does have high chemical potential, it's crossover, and it doesn't tend to give rise to any interesting signals in gravitational waves or the like. There are some people who have suggested that you might be in a region where you did have high chemical potential at those temperatures, and so you could see a first order transition, but it's still very hard to see signals persisting to the present day. It doesn't tend to affect Big Bang nucleosynthesis or the like. But we certainly went through it. We got here.
that we had enough questions now. So Professor Pisarski will give tomorrow another more dedicated seminar to the phase diagram. In case, so you are invited to attend, and otherwise, let's thank Rob again and close the session.